Just going to keep adding some more stuff into our linear regression discussion that we've been having. Hopefully, especially for kind of that individual assignment, but also I think some of the Connect assignments, you've figured out how to get that data analysis tool to work. If you haven't done that yet, try to at least get it on to Excel to make sure that, I know if you have a Mac, some of the older ones, it's a little bit tricky. And so if you're having issues with it, like reach out to me. If you're not able to kind of figure out how to get that added in. Like I said, I know for the older Macs, you even have to kind of download this Stat Plus thing. And then it works kind of just like we've been doing it in class. We're kind of getting it added in there. I want to make sure everybody has that. Okay? Any questions for me before we kind of get going here? Good? All right. So, we've kind of already went over this a little bit, but just to be a bit more, I guess, explicit about it. We've already used these in some of the regressions I've shown you, but if we're not dealing with a normal variable that's kind of continuous, but instead kind of a binary variable that's just a 1 or a 0. So this would be like something like we're identifying, in the example we did, if they were an athlete, it was a 1. If they weren't, it was a 0, right? Or maybe we had a gender variable where it was 1 if male, 0 if not. Maybe it's even just an indicator, is the person over 60? 1 if they are, 0 if not, right? So the way we interpret these variables, like the way that would kind of look, I mean, we would write it in the same, I guess here I'm just calling it the variable D, which is its dummy variable, right? So it's a binary variable, we call them kind of dummy variables, right? If it's a 1, it kind of clicks on. If it's a 0, it clicks off, right? So we're thinking about if we were to look at, say, the relationship between X and Y, but we also have the relationship between this dummy variable and Y. Okay? So we interpret it the exact same way. It's a 1 unit increase. Just now, if it's a dummy variable, the only unit that can increase is going from 0 to 1, right? Which would go from belonging to whatever group, right, is the 0 to belonging to the group that's a 1. So if we were to look at a non-athlete, if we were to go from a non-athlete to look at what the GPA of an athlete would be, or the effect of kind of not being male but being female, the effect of being not under 60 but over 60, right? So we can kind of give a nice visual interpretation as to what this dummy variable is really telling us. So let's say, we're trying to find this line of best fit for this relationship between X and Y, right? When we add in that dummy variable, essentially we're going to get a different prediction for the group that is the 1 for that dummy or that binary variable. So I'll kind of show you why. We can think about it as what we're really saying is whatever group is the 0 for that dummy variable, there is a relationship between X and Y, and we could draw that line of best fit. For the second group, there will still be that same relationship between X and Y. It's just that where that group starts out at might be a little bit higher, might be a little bit lower. So why is that the case? So if we think about when we're trying to predict Y, right? Once we have our estimates for what the coefficients are, we would have kind of this intercept. We then would have the estimate for what that relationship between X and Y is. And then we'll call this BD. We'd have the kind of effect of that dummy variable on the predicted Y value. So if we're thinking about the relationship between X and Y, right? If we tried to predict kind of where the group that is a 0, where that line of best fit is, well, where would it start out at, right? What's the kind of, when X is equal to 0 and the dummy variable is equal to 0, what would our predicted Y value be? The X variable is 0, and that dummy variable is 0. What is the predicted Y value? Yeah, just the intercept, right? The constant, the prediction that we have for that. So I think about, we're going to start out here. Okay? And then if the dummy variable is 0, as we increase X, we could come up with predicted values for Y. So we'll assume there's kind of this positive relationship. So really this predicted Y value was just the intercept plus this, right? Because when the dummy variable is equal to 0 for that group, there's no additional component. 0, it doesn't matter what the coefficient estimate is, 0 times anything is always 0. Now, if we're looking at the group that the dummy variable identifies with a 1, where would it start out at? Well, when x is equal to 0, it would be the intercept, but now it's this kind of additional intercept. You can almost think about it as. So for that group, we're starting out with the intercept plus whatever that coefficient is. Actually, I wrote the dummy variable in here, but it's going to be 1, so 1 times anything. We can kind of simplify that. So they start out a little bit higher, but notice that there's no kind of like interaction between that dummy variable and this x variable, so the slope would still be the same, right? So we can really think about it as almost like a shift in this line of best fit for belonging to whatever that group is, okay? Any questions on that? So that's kind of where that comes from. Maybe it's a nice visualization of how we can think about this dummy variable is really just changing our kind of predictions for y. Right? So, we do the exact same tests, right? We could do a right, left, or two-tailed, but we're always going to do just like we did for the slope coefficients. It's always, is that coefficient equal to 0? Like that's what we assume. What we're trying to show is, can we find enough evidence to reject that hypothesis? So here, this, kind of gamma 0, this is always going to be 0. We're always testing for whether or not that dummy variable kind of coefficient is not equal to 0, so we assume that it is. Right? And then it's just take that coefficient that you have, divide it by your standard error. It's the exact same thing as we were doing before. We really can't just treat it like it's any other coefficient, right? There's basically no difference, right? So, we could walk through all these steps, same kind of way. We would come up with a test statistic. We already mentioned, Excel does all this for us, right? So I'm never going to make you kind of work this one out by hand. We just have that test statistic. We'll be given the p-value from Excel, right? So you already looked at an example last class of that athlete variable, right? So there shouldn't be anything too crazy. What happens if I have a dummy variable that isn't just binary, but it takes on different values for several different groups? If I can get this to work. There we go. So what we're going to do there is we're going to create a dummy variable for every single possible group and then leave one of them out, right? So you can kind of think about it as I'll have several dummy variables, but one of, right, those groups, I'm not going to include a dummy variable for, right? So this would be something like, let's say I want to do, I think I'd use education later on. So let's say I want to know the effect of being a freshman, sophomore, junior, or senior on someone's GPA, right? Well, I might want to put kind of an identifier for each one of those groups. So 0 if you are not a freshman, 1 if you are. Then another dummy variable, 0 if you're not a sophomore, 1 if you are. Junior, 0 if you aren't a junior, 1 if you are, same for senior. I wouldn't include all 3 of those dummy variables in my regression, because then that would imply that there is a person for which they could have zeros for every single one of those. Well, no, you have to belong to one of those classifications, at least, in terms of how the university views you. So you want to make sure that if you see all zeros for the dummy variables you included, you have to have one group that would be kind of reflecting, let's say I leave out freshmen. Well, now if I am a freshman, the dummy variables for sophomore, junior, and senior would all be 0 for me. And then I would kind of be that group that's not in the regression equation. So now the way I can interpret each one of these coefficients would be, well, if I am a sophomore, there's a 1. So the coefficient on sophomore would be, here's the kind of additional increase or decrease in predicted GPA if I'm a sophomore relative to being a freshman. And then for the junior variable, if it was a 1, if I'm a junior, the coefficient is, this is the effect of being a junior relative to that group I left out, so relative to being a freshman. Right? So that's kind of how we make the interpretation when we have multiple kind of categories. Right? So each dummy variable there would be the kind of change, the predicted change in y from belonging to whatever group that observation had a 1 for, relative to the group I left out. Okay? So let's think about another example, which is years of schooling. I think this one also kind of hits on sometimes it's better to leave certain groups out, right? It makes our coefficients make a little more sense, right? So let's say I've got some like when I download the data, it literally just says education, and it just says high school degree, some college degree, or graduate degree, right? Well, what I'm gonna do is, which one of these kind of makes most sense for me to leave out? If I create a dummy variable, I could create them for, one for whether someone had a graduate degree or not, one if they only had some college or not, right? So these aren't like cascading. You couldn't, high school degree here is that you only have a high school degree, right? And then some colleges, I kind of have some college, I'm not counting as just a high school graduate anymore. So which one might make the most sense to leave out here? Remember, these coefficients are always going to be interpreted as, say, the effect of having a graduate degree relative to whatever group I leave out. So what might make the most sense? What group should I kind of leave out of my regression there? Yeah. Yeah, right? It probably makes most sense if you think that one of the groups is going to have the lowest to leave them out, and then every coefficient is, well, here's the additional income that you could, maybe expect from having some college. Then what's the additional income from having a college degree? What's the, you kind of want it to kind of your coefficients to be growing. Now, if I'm comparing like to the college degree, well, now these are going to be probably negative coefficients. This one will be positive. So probably leaving out kind of whatever that lowest or sometimes whatever the highest category is, right? If I left out graduate degree here, then my interpretation would be something like the effect of having a high school degree relative to someone who has a graduate degree. And I'm thinking about maybe the effect that has on income. Now my coefficients I'm going to be seeing will be kind of these negative values, right? So you've got to think about kind of the context of your example, which group makes the most sense to leave out. And there's no right or wrong group to leave out. Like the regression will still run. It's just the interpretation will be a little bit clunkier if you choose a group that doesn't make sense in the context of your example. So we'll work through some examples here. So if it isn't ordinal, kind of leaving out that lowest or highest category, right? If it's not ordinal, use your best judgment. So I'll give you an example of a couple here. So the one that I kind of grabbed some athletic revenue data. I had some like subsidy data, how much like students are paying for athletic programs, which is kind of interesting. We'll probably use that for a couple other stuff, other examples I'm going through. But maybe we think that, universities, the whole reason, look, COVID is like not in a great place right now, and we're still playing sports. Why? Because there's a lot of money, right? Like this raises a ton of money for universities through, not even just like attendance. Ticket revenue is actually probably for most universities not even close to the highest kind of source of revenue. You got to look at kind of what their TV contracts are with that the conference has with ESPN or all these other organizations, and so they want to make sure that that's why Ball State plays on Wednesdays, right? Because they can actually, someone actually wants to kind of pay them to kind of be on at that time slot. There's no other competition, okay? I don't know why I had to dog on Ball State. The MAC is great, but like they're not going to be able to compete with like the SEC school teams, right? So what we're going to do is we're going to have all these different conferences. We could do this for football. We could do this for basketball. We could do it across kind of sports, right? So it's just how much money is being raised. And if I belong to a larger conference, maybe I see, that school has a larger amount of revenue, right? So I kind of had all these different conferences that your school could belong to. And I created dummy variables. 1 if that school belonged to the ACC, 0 if not. I then am thinking about, okay, what is the impact of belonging to one of these different conferences on that school's athletic revenues, kind of overall sports? Right? Well, I had to leave one school out here. I believe I left out the American Athletic Conference. I tried to choose one that I thought would have one of the lower revenues. You'll see I got it wrong, but that's the one I left out. And I'll kind of show you here, it's not necessarily ordinal. I may not know exactly how the conferences kind of rank. So I ran this regression, right? My Y variable is revenues. I then had all these columns in Excel that just represented kind of the dummy variables for what conference that school belonged to. And kind of what I found here is, right, here's the intercept. So you can kind of think about here is a kind of a weird interpretation. And I actually kind of see it kicked out kind of I had it shown down here, it left out the American Athletic Conference. But each one of these coefficients can be interpreted as the change in predicted revenue for a school belonging to the Sun Belt Conference relative to this conference that I left out. So relative to the American Athletic Conference, if a school belonged to the Sun Belt Conference, their predicted revenues would be about what? $25 million lower, right? If they belong to the Big 12, relative to the American Athletic Conference, their predicted revenues would be $52 million higher, right? So based off these coefficients, right, could you tell me what conference, if I have to look at one school belonging to a conference, which one would have kind of the lowest predicted revenue? Remember, I can only belong to one of these conferences at a time. So anytime I belong to a conference, every other variable would be equal to 0, right? So I'm really just looking for what's the kind of lowest coefficient here, negative 25 million, right? This would be the conference that has kind of the predicted lowest revenue, right? Because if I belong to this conference, well, now it's 1 times that coefficient, right? If I think back here, if I belong to, well, I didn't have them here, but if I belong to that Sun Belt Conference, and it's 1 times whatever that coefficient is, and so if it has kind of the largest negative coefficient, it's going to have the lowest predicted revenue. And then which one will have the highest? Well, there I'm looking for what has the largest coefficient, right? I think it's SEC here, right? So then if they belong to the SEC, now that variable is 1, every other variable is equal to 0. So 0 times beta 1, 0 times beta 2, but they belong to the SEC, so 1 times that coefficient, right? So the predicted revenues will be kind of highest for the SEC there. So if you do had an example like this, based off my coefficients, I could kind of rank which of these conferences would add the most predicted revenue if I belong to it, right? So if I'm a school, and I always kind of in this example use the, so I have like independence here, but I always use the example of like Notre Dame, like when they're thinking about joining a conference, they might have ran a regression like this, controlled for a lot of other things, but looked at and said, okay, which one of these conferences would kind of change our predicted revenue the most? Okay. Any questions on that? Okay, so here's a slightly tricky one. If I left out the American Athletic Conference here, what would the predicted income be for a school that belonged to the American Athletic Conference? Yeah, just the intercept. Because every other dummy variable would be equal to 0. So 0 times, it doesn't matter, because 0 times anything is 0. 0 times, doesn't matter what that coefficient estimate is, because anything times 0 is 0. Add all those zeros up, all I'm left with is whatever that intercept is, okay? So whatever group you leave out, the intercept there would essentially be kind of their predicted Y value in this case, predicted revenue. Okay? And so we kind of already talked about all this. So go through another example. So let's say I've got dummy variables for whether an individual is white or non-white, and kind of then what their gender is, right? So if I include a dummy variable for white and male, then this is going to determine, like, okay, if the individual is male, kind of what is the kind of predicted Y value? Because that, if it was a 1, it kind of turns that coefficient on, right? Turns that, kind of adds that into the equation. And then I kind of have, maybe if it was kind of a white male, right? Each one of those coefficients becomes a 1, and so they get added into the prediction, right? So I could start to kind of use multiple dummy variables that don't kind of belong. It might make it a little bit harder if it's not all representing kind of one thing, like which conference you belong to. I now have 2 dummy variables identifying kind of what, 2 different characteristics. Okay? So what I could do there is just think of all the different possible combinations. Right? So maybe I'm thinking about there's race or gender discrimination going on with wages, right? And so I might want to say, okay, well, if someone fits this kind of gender and race category, how much predicted change will we see in their income, right? Now, hopefully these are all 0, but we probably know they're not. So what we do is come up with every combination. So I create an indicator for, is the person a white male? 1 if they are, 0 if not. Are they white female? 1 if they are, 0 if not. kind of think about here, you know, if we want to make this, if we only had white and black individuals, we could make this kind of non-white, right? Male and then non-white female. Okay? So then we kind of can interpret all these coefficients as relative to whatever group I leave out, I have to choose one of these, right? Probably what makes the most sense if we know anything about kind of gender and kind of race, you know, wage differentials, probably leave out kind of the white male category, and now it's relative to that white male, what's kind of the wage disparity that exists from belonging to one of these other categories. Right? So we can start to answer some pretty, you know, interesting questions using these dummy variables. Okay? So similar idea. I'm going to push it a little bit further on this one. And I think, let me see, I'm pretty sure I have the data here, so maybe I'll actually show you this one in Excel. Traffic stop. Did I put it in this? No. I think it's in one of my old ones. So let's go here. No, I've got it floating around here somewhere. Where would it be? Sorry, I thought I had it in your folder, but apparently I don't. I know I have it somewhere else in this drive, and it's really interesting, so I'm going to show it to you. Oh, here. Let's get that opened up. And that only opened up the results. So let's go. Let's try this one. It's pretty big. It's not the one I want either. Well, maybe I'll just show you the results. I wanted to kind of walk through it in Excel because I think it's kind of interesting. Here we go. So I had this traffic stop data, and it's undisclosed, but it's a large city in southern Texas. I'm guessing Houston. So you've got kind of a bunch of information on every single kind of pullover, whether or not a ticket was issued and whether or not the individual ended up being arrested from kind of this traffic stop. Right? I also, you get driver's age, the number of years the officer served. You then have kind of these identifiers for was the driver male, was the officer white, was the driver white, and then kind of was the officer and the driver non-white, right? So they were all kind of coded as a race variable, so I had to kind of create these dummy variables. You can kind of now imagine, like if I have kind of, is the driver male or not, is kind of, I have the race identifier of the officer as well as the driver. I could come up with these different combinations to see if, well, if I'm, you know, non-white and I get pulled over by a white officer, am I more likely to be issued a ticket, right? So here we're thinking about this ticket variable being our Y variable. Okay? So I've got this kind of set up to be, is the officer white and is the driver non-white? I've got is kind of these, it's just the driver white and it's just the officer white. So I think one of these, let me see. Well, I think I have the results look a little bit better here. So we'll get the slideshow of it. So essentially what I did was think about the different combinations of kind of driver and officer kind of race. And when I say race here, we're really just breaking it down to white, non-white. Okay? So there's kind of some additional X variables I include in here. I believe I put in driver's age, right? I think I also put in the officer's years of service, right? Those are probably two things that might help predict, right? You know, because there's tons of different reasons why someone can get pulled over, right? But maybe this captures some of those reasons, or maybe officers of a certain years of service are more likely to issue tickets, right? So I included those as kind of some additional control variables, right? Excuse me. And then I have the different combinations of dummy variables. So the one would be, is the officer white and is the driver non-white? I then have, is the officer non-white and the driver white, right? I then have, are the officer and the driver both non-white? So the group I left out here was the driver and the officer both white. And then kind of the other dummy variables are the different combinations. So maybe it's not that we see just discrimination going kind of one way. Maybe it's if like the race of the driver and the officer don't match up. Maybe we see discrimination working kind of in both directions. Hopefully not, but we'll see, right? I then also had that additional variable in that data set, which was a 1 if they were arrested and 0 if not. So we can kind of look at like different dimensions of possible discrimination, right? I mean, even if we don't see differences in the amount of tickets issued, if we see a difference in the amount of arrests, well, that's even more alarming, right? So I kind of ran both of these kind of regressions. So we'll look at this here. So even controlling for the driver's age and the officer's years of service, which we thought they might matter. And yes, these coefficients are kind of small, but look at this p-value, right? They definitely are significant, right? We can definitely reject the null that there's no relationship between getting a ticket and kind of your age and the years of your officer's service, okay? One thing I kind of found interesting was the sign of this, though. So if the officer has served longer, they're more likely to issue you a ticket if they pull you over, which is kind of interesting. Also, as you get older, you're less likely to get a ticket. This definitely holds true in my life. So if we look at these dummy variable indicators, right, the officer and driver kind of are both non-white, right, relative to if they were both white. There's a pretty significant increase in our Y variable. Now, here's one thing where talking about dummy variables, this is the first, I think the first example I've shown you where that Y variable is dummy. It's a binary variable, right? You either get a ticket, 1, or you don't, 0. So now if we're thinking about this predicted Y, and let's say I use that kind of, whatever that dummy variable, that's a 1. Well, the way we interpret this coefficient now is, well, this is going to be the change in my Y variable if that dummy variable is equal to 1. But if I think about predicted changes in Y, if Y is either 0 or 1, well, basically what you're saying is the change is in the probability that this is a 1 as opposed to a 0, right? The probability that I get a ticket, right? So it's because if you think about the units, right? Usually it was like, well, we would expect $250 higher, or we would expect, this to go up by, however many dollars of revenue. Well, now what's the units if I just have a 0, 1 variable? The units are essentially changes in the probability, okay? So like if we see 0.09, that means the predicted probability that I see this variable go from 0 to 1, or I get a ticket, goes up by about 0.09, which if that's the probability, 9%. Okay. So if we look at these results, relative to a white driver and officer, a non-white driver and a non-white officer, the probability someone gets a ticket is about 0.18 higher, or 18% higher. If the officer is white and the driver is non-white, there's actually kind of a much relative when they're both white, much smaller increase, right? That non-white driver is still 6-7% more likely to get a ticket, but not that kind of 18% change. So there might, this might be evidence that there is some discrimination going on from white officers to non-white drivers, but it also looks like kind of non-white officers are also kind of discriminating against non-white drivers. And if we then look at kind of when the officer is non-white and the driver is white, well, now also looks like there might be some cross-race kind of discrimination going on here, where the probability is about 17% higher, a probability of 0.17, if the officer is non-white and the driver is white, relative to if they were both white. Right? So we can start to answer some pretty interesting questions. Now, don't buy too much into these results, right? I don't have control for a lot of things, right? So, I would probably want to control for like the area that the stop took place in, right? Maybe the socioeconomic, average income or unemployment rate of that area. And maybe I want to, even if I look back at that data set, I'd have to do a little bit of cleaning, but the original file had like the reason for the stop. These numbers all represent something. So 7 is probably just like a small traffic violation. If we go down here, do I have anything other than 7? Oh, maybe I deleted all the ones that weren't. Yeah, so I think I just took out the the ones that were kind of just general traffic stops. But, you know, if I had more information, kind of the result, you know, some of this, you know, I don't have a lot of other information about the individuals or the officers here. So this isn't great. I would love a lot more control variables. So we got to be careful interpreting these results. They are just correlations, not necessarily causal. So although this looks alarming, maybe that there is some discrimination going on, how much of the Y variable have I explained? R squared tells us that. I've explained 3%, right? 0.03. So there's a lot out there that I'm not capturing. So let's, you know, but this is an example of the kind of questions you could answer, you know, using regression. Okay? So we did the same exact thing, but now I kind of used that Y variable, which was whether or not they got arrested. Notice, once again, before we interpret these, my R squared is even lower here, right? So, I mean, whether or not you get arrested from a traffic stop, not able to make very good predictions. We're only explaining 0.2% of the variation in whether or not you get arrested from a traffic stop. And if I kind of look here, I have some coefficients and I could interpret them, but if I look at these p-values, they're all greater than 0.1. In fact, these are enormous, right? 0.7. So my p-value is not going to be less than alpha, so I fail to reject the null. And remember, kind of our null hypothesis is that these coefficients are equal to 0. So if I fail to reject that, I'm really saying I found no evidence in this data set that there's any effect of kind of the, you know, combination of driver and officer race on whether or not someone gets arrested when they're pulled over. So I guess that's, you know, good news. I mean, that's definitely good news. But right, we had some evidence here that there might be some discrimination on kind of issuing tickets, right? So, so kind of interesting, you know. And if we really look at this data set, the reason why we can get some really low p-values, like some of those p-values are 0. I think I had like 22,000 observations, right? So if we go back and look at from last class, I think I had this on the slide. I know it was back here somewhere. Here we go. Remember, this was kind of the equation we had for the standard error. We didn't have to remember that, or, you know, memorize this or anything. But notice, if my n goes up, what happens to my standard errors? My sample size gets higher, this standard error goes down a lot. If my standard error goes down a lot, what happens to my test statistic? In absolute value, it's going to go up a lot. Higher test statistics, if we just think about this as from like every other distribution that we've looked at, if I get a test statistic way out here, the p-value is going to be much, much smaller. So when we take really high sample sizes, we have the ability to like be more likely to be able to reject kind of that null hypothesis. But even with all that power, even with that huge sample size, if there is no effect, like we had here, I still am getting these pretty large p-values, which means the likely effect is 0, right? Because I have this huge sample size. If there was any effect, I was able to reduce my standard errors and kind of get these, should have been able to get a p-value to where I could have rejected what I assume to be true. Right? But in this case, I can't. And then, you know, once again, we have our p-value output here. Remember, anytime we see this e to the negative, right, these are significant. Right? So, because this essentially means the p-value is 0. Also, this is beside the point, but always, this is why I love regression, because like you can kind of start to look at some interesting stuff, but how would you kind of interpret this coefficient here? So if this is the driver's age, it would be a 1 unit increase in that variable. So every year older you get, the change in the predicted Y variable, which we said here, because it's a binary variable, the units of the Y variable are, it's like probability. So for every year the drivers got older, the probability that when they got pulled over, they got arrested was going down by a pretty small amount, but what, 0.0002 is a probability, so 0.02%. Basically, when you're younger, you probably do dumber things, right? But the interesting thing here, because that was the same case with getting a ticket, right? But the interesting thing here is we also found that it was a significant effect, right? We could reject that the relationship was 0 between an officer's years of service and whether or not the person was arrested. Well, for the ticket, we said the older the officer is, the more likely they are to write a ticket. I don't know if this is like a crotchety old man thing or what the whole story is behind it. But the interesting thing is the probability that you get arrested from just a regular old traffic stop, the more years of service goes in the other direction, right? So it's almost like they know they need to be issuing you tickets, but they're also not near as likely to kind of like freak out, go extreme and like arrest you, right? So you know, it's just kind of interesting the way if we think about how we interpret these coefficients in these different examples. Okay, so I think, you know, we kind of have a summary here if we're kind of looking back and trying to remember how we interpret some of this. And a lot of this is me kind of talking. So if you have any questions, anyone at any point here, you need to kind of jump in because, you know, a lot of this exam, the final, we're looking at these linear regression results. It's a lot of interpretation, right? Like how would we interpret this coefficient, right? Can we, based off the p-value, reject kind of that there's no relationship, right? That null hypothesis that that coefficient is equal to 0. All right, so I don't remember if I don't think we got to watch that video. I think I might have given you the link and told you, but it was like, it was a Comedy Central with Jon Stewart, and he's looking at this real economy, like it was a real, it wasn't a like bit. Well, I mean, it was a bit, but I don't think the economist was so much in on it, where he was like ranking people from 1 to 5, kind of based on their looks, and like seeing if that could predict kind of changes in wages or changes in like all these other like number of applications that they got callbacks on, all these different things, right? So kind of one of the things that came out of this study is that potentially kind of this looks variable or this kind of idea that someone's attractiveness might in fact influence wages, and that might be different for men versus women. Right? So how could I use linear regression to understand this? Well, if I've got this regression where I'm thinking that I want to try to predict wages, I'll have my intercept, and then I say, okay, maybe I have this kind of like attractiveness variable that I think has some effect on wages, and maybe I think maybe just kind of there's some wage disparity, right? Like a wage gap idea of if the individual is male, maybe that changes the predicted kind of wages. And actually, I think the way I have to set this up on the slides, just to kind of line up, let's do it so that the binary variable is 1 if they're female, 0 if not. Well, this tells me the kind of change in the levels of where the wages might start out at for males versus females. But it doesn't tell me that maybe this X variable has a different influence on my Y variable for the 2 different groups, right? Because remember when I had that graph earlier, I told you a dummy variable really just gives you like a shift, right? They still have the same slope. So what I might be thinking about is maybe this X variable of attractiveness, when it comes to my Y variable, maybe for males, right? Even if they both, let's assume they both start out at a kind of similar base. Now we know that's probably not true in practice, but let's assume that both males and females have the same intercept here. So essentially like B2 here is almost 0. Okay? Well, it could be that the relationship between attractiveness and wages is a pretty low slope, right? Not much of a relationship for men, but maybe it has a much greater impact for females, right? Maybe these employers are creeps, right? So we've got, maybe we want this difference in the slope. So how do I get this difference in the slope? What I actually do is I include this third variable, which is the interaction between this dummy variable and the variable X that I was interested in. So now, when I try to predict the slope, right, for what's the relationship between attractiveness and wages for men, well, for men, this would be a 0, this would be a 0. So these 3 drop out. Now the only thing I'm left with for the relationship between attractiveness and wages for men would just be that coefficient B1. Now if I want to predict what's the relationship between attractiveness and wages for women, if we get a 1 plugged in here, Well, now the effect of attractiveness is B1, but because this is 1 now, it's B1 plus B3, right? So my slopes here would be something like this. And I'm assuming that this is that B3 is positive here only because I know kind of the end result of what this study found. So to find kind of differences in the slope for two different groups, we have to take that dummy variable and interact it with our x variable. Okay. So, okay. So we have something that looks like this, right? Our kind of final regression. So we can think of B1 is just kind of the overall effect of attractiveness on wages across genders. Beta 3 is the additional effect for females, right? Now, if I want the total effect for females, that's where I added B1 or beta 1 to beta 3 or B1 to B3. But the way we would interpret beta 3 or B3 here is it's the additional effect of this kind of beauty variable on wages for females. Right? So the sad thing is kind of, if we looked at, and I think did I talk to you guys about this example at all? A little bit, can't remember. So the idea was like they sent out all these otherwise identical applications, and somehow it ended up with like they had pictures attached to it, or like something about the LinkedIn profile I think they could observe. And so then they had some kind of measure of attractiveness based off of like random people they selected to like rank these people and came up with an ultimate ranking. And they found that the applications that were kind of sent out with higher attractiveness score were much more likely to get callbacks or kind of get interview requests from these applications. Right? So when they looked at and they estimated these relationships and then kind of draw these lines of best fit, for men, it was like, right there, it's positive, but really small, right? So there is some link between attractiveness and kind of this, not wages, but here it was the number of interviews for men, but notice kind of for women, how much higher that was, right? That kind of effect of kind of being ranked in a higher attractiveness percentile had a huge impact on the number of interviews they got. So, you know, this is a bad thing, right? Like this is like something that should not be factoring in to the equation. We can kind of show here, not only should it not be factoring in, there's differences in how this affects the two genders, right? So I don't know, I thought this is a kind of interesting example. And it's a really good example to start to think about if we want to estimate differences in slopes between two different groups, all we have to do, take that variable we're interested in and interact it with whatever that dummy variable is for whatever group we're looking at. Okay. Any questions on that? So we're thinking about here, kind of B2 is going to be kind of the shifter in that line of best fit. And B3 is going to be kind of changing the slope of that line of best fit for whatever group is that one in the dummy variable. Okay. All right. So actually, I'm going to kind of go a little bit off script here. I'll show you an example because I just had it off the top of my head. So let's say we had that GPA data, right? And I don't know what's going to come out of this, so I'll apologize. I don't know what the results will be. So I'm going to put this on a different sheet just to, I'm going to select those first four variables, make sure that we can see this, okay? So I'm trying to predict, that's way too bad. Oh, not 1500, right? There we go. If I'm trying to predict GPA, so that's my Y variable, and let's say I want to know what's the effect, kind of the SAT score, how much does it predict the GPA goes up or down? Right, so that's my X variable. And let's say, I'm going to delete that high school rank. I have this dummy variable athlete, right? So what I can do, right, if I think that maybe the SAT score is a better predictor for non-athletes than athletes or vice versa, I'm going to need to create that interaction term, right? That dummy variable multiplied by the X1. So I'm kind of think about this as I'm creating my interaction term, right? Or if I wanted to, this is SAT times whether or not the person was an athlete. So I'll take the SAT, multiply that by whether or not they're an athlete. Hit enter. Now, a nice little trick if I want to do this, instead of dragging it down, if I double left click this little like green box here when my mouse becomes an arrow, it'll do that for every single observation in my data set, right? Now notice, when I created the interaction term, whenever someone wasn't an athlete, that was just a 0, right? Which makes sense. Once athlete is 0, the interaction should be 0 as well, right? So it's almost like Excel's only estimating the additional impact of the SAT score within just the observations that are athletes, right? With this third interaction term. Now I go to data, I go to my data analysis, I'll go up here, no, not up here, I'll go down here to regression, hit OK. My Y variable is this GPA, right? And then my X variable, scroll up here, I'm going to include the SAT score, athlete, and then that interaction term. So select them, Control-Shift-Down arrow, or Command-Shift-Down arrow on a Mac. I selected my labels, so I need to make sure I hit that. I'm going to put it on a new worksheet. Hit OK. So here's my regression output. So we'll notice we're explaining about 16% of the variation in GPA, so not as bad as other examples we've seen, but not as great, as it could be. And then look down here. So the way I interpret these results are first of all, that p-value on whether or not there's a relationship between the SAT score and GPA is almost 0. So I for sure found evidence that there's a significant relationship between the SAT score and GPAs. The athlete variable, not quite significant. These p-values are pretty high, so not really even close to significant at any levels we usually look at. But let's just assume that they were, and we'll kind of interpret what they would mean, the coefficients would mean. So on the athlete variable, this would predict that if the person was an athlete, their predicted GPA would be about 0.06 points higher. Right? So this is kind of our shift in that predicted line. However, the predictive power of the SAT score, or the relationship between the SAT score and GPA for athletes, actually makes that SAT score less predictive of what their GPA will be, right? So the total effective GPA here for athletes would be the coefficient for the SAT score plus that coefficient for the interaction term, right? So notice that's going to be a little bit lower than that kind of slope of the line between SAT scores and GPAs for non-athletes. Okay? So this is kind of how you would in Excel, you would include this interaction term, you essentially create this new column, you can throw in your regression, and then you've got your coefficients there you can start to interpret. Okay? Questions on that? Okay with that? So I'll put up an online quiz today. It's probably just going to be what kind of examples you guys might want to see, because we're just going to keep going through regression stuff from here on out. And I'm trying to think of kind of, things that would interest. I want to make sure that things that I find all this stuff interesting, but you guys might not find those particular examples. So I'll give you a couple different options of some data sets that I have, and try to come up with some examples for what we're going to be working through with those. Okay. All right. We'll see you guys on Friday.